In this sequence, I'd like to go over a little bit of a debugging case study, examining where things went well and where things went wrong. My first build on this kind of device was to turn my refrigerator on and off in my office so that I could make videos without too much background noise. That humming noise you hear in the background is my fridge. And I need to be able to turn it off to make videos and yet be able to have it come back on automatically. So I put this little gadget together. And when I push this red button, the little red light there will go out and stay out for a while. That indicates that this solid state relay has been switched off. And eventually that light there will stop flashing and it'll turn back on. Or I can turn it back on immediately with this button. And we see the little red light comes back on. Now when I went to implement the second version of this, I didn't have a Pro Trinket microcontroller like I used on the first version. So I picked up this Feather M0 that I just happened to have sitting in my on my shelf, and tried to implement exactly the same process with that. So this pin here, I'm turning on and off under digital control according to what I do with pushing the button. And that's providing, this is a 3 volt microcontroller, so it's providing a 3 volt signal over here to turn the SSR on and off. So I push it briefly and it'll stay off for a short period of time. So the voltage here is now 0, and eventually it'll switch back up when the light comes back on. Now, part of the problem is I noticed there was some strange behavior in the way it was operating. It didn't seem to be quite reliable, and there were a couple of things going on. I checked voltages all the way around, and eventually I wound up looking over here and I found I'm only getting 2.6 volts. But this is a 3.3 volt power supply. If the voltage is dropping that much below what it should be 3 volts, then maybe I'm drawing more current than this device can supply. I'll just take that lead out of there and plug the multimeter in here. So without the SSR connected, I'm getting 3.14 volts, almost the 3.3 volts that I would expect. And if I switch it off, it goes down to 0. Switch it back on, it comes back up to 3.1. So why am I not getting as much voltage over here at the SSR as I was expecting? Well, if I went back and looked at the specifications for this solid state relay, I would see that it needs about 5 milliamps of current to actually activate it. When I've got this plugged in, it's showing that it's activated, but at this low voltage, I'm not getting all of that 5 milliamps of current that I would expect to. I went back and looked at the specification sheet for the product sheet from the manufacturer for this board, and they said I could get 7 milliamps out of it. So that shouldn't have been the problem. I used my multimeter and measured the actual current I was getting. Switch to the 200 milliamp scale and plug this into the current measurement socket. Right now I've got no current flowing. Let's measure between this location and the solid state relay. I've only got 3.8 milliamps of current being supplied, and that's at that low voltage. I should be able to get 7 according to the spec sheet. So what's wrong? And what am I going to do about it? I put together this test rig with exactly the same microcontroller to see if I could isolate the problem. I've got ground here connected to one side of this resistance. I've got the output pin that I'm using over here connected to the middle of this potentiometer, and then connected to the other side of the resistance. So I'm putting a variable resistance between that pin and ground. And by adjusting the position of this potentiometer, I can change that resistance. This allowed me to alter the resistance from, well, that's 2,000 ohm resistors in parallel, so that's a 500 ohm resistance. I could start at 500 ohms as the lowest and go up pretty much as high as I want with this 10K potentiometer. What I found was that at high resistances, I still got the higher 3.3 volt output, but at lower resistances, I was getting more current flowing, and this voltage was dropping. And it dropped down to about 2.5 by the time I got 5 milliamps flowing, and I thought I'd better stop there so I didn't fry the board. So now I know that this chip isn't living up to what it's been advertised as on the product page. So I set out to make a workaround, and how can I solve that problem? If I don't have enough current to switch this on and off, maybe I have enough current to switch a transistor on and off. So I found room on my board to add this transistor and a resistor to that transistor, and I can use that transistor as a switch. So what I'll do is I'll connect the positive side of my solid state relay just to my positive power supply, and I'll connect the negative side to the input of the transistor. So now I see it's on, switch works to turn it off. I find I've got 3.1 volts coming out of my port. So I'm not drawing as much current, I'm still getting a good output voltage. Over here, I'm also back up to having the full power supply voltage. So I've temporarily solved my problem by using a transistor that doesn't draw more current than this little board can provide. Now I've made that small but all important modification to my code, and the program's still working the way it was before, switching the solid state relay on and off. And let's go and see what's happening on the output. If I look at my output pin, the solid state relay on, I've got about 3.25. With the relay off, I've got 0. So that's as it should be. Everything's working the same way it was, and I've got this transistor switching the current flow through the solid state relay. But if I've got a higher current output available at this pin now, maybe I can switch back to just having that pin directly drive the solid state relay without getting current overload. So I'll disconnect that from there. I'll connect the low side directly to the ground. And if the high side is just directly connected, then the solid state relay will be on. If it's disconnected, it'll be off. Now I'm going to go over here and try plugging it directly into the pin, the way I had it before. It's performing just the way it did before. I'm getting it to switch off, and eventually the red light will come back on. It'll switch on. Now the relay has switched back on again, and we see 3 volts going into the SSR. So now we don't have that much reduced voltage of 2.5 volts. We're getting enough current supply to adequately switch on the SSR. So we've switched up to the high current mode, and I'm no longer alarmed at the way this is operating. By switching up to the high current mode, I don't need this extra transistor in here to allow me to control that output. This was a really simple fix that took only really one line of code to change the behavior of the microcontroller to make things work properly. However, finding out which line it needed to be was a real chase through the data sheets. And I'm going to try to lead you through that process so you can see how I got from point A to point B, and maybe you can do the same kind of thing. So I wanted to find out something about current capabilities, so I opened up the data sheet and searched for current. And that gave me a whole lot of choices over here. Eventually, I decided I'd try searching for current and GPIO pins and see what that found me. And that got me a more limited selection. Eventually, on page 1067, I found this stuff about electrical characteristics. And I'm interested in device variant A here. And that tells me that, some absolute limits on supply, but it also tells me that the maximum source current is about 14 milliamps per cluster. And a cluster is a group of output pins, as shown in table A3. I searched further and eventually found this table about input-output pin characteristics. It tells me a bunch of things, including the amount of current that I can get out from one of these pins if it's set to the high voltage level, the power supply voltage. And it says that if I've got a power supply voltage of 3 to 3.5 volts, I should be able to get 7 milliamps out of the port. And that's exactly what all of the product data sheets tell me. But there's some fine print here. If I've got that supply voltage and the drive strength is set to 1, then I can get 7 milliamps. If I've got that voltage, but the drive strength is set to 0, then I can only get 2 milliamps. That would seem to be what's happening with the setup that I've got. I'm not getting as much current as I thought I should get. So I think maybe somewhere this drive strength is being set to 0 instead of being set to 1. How can I overcome that? When in doubt, Google or ask questions in an online forum. Even a limited response can point you in the right direction and let you know that it's not a solved problem. After a lot of chasing around, I found myself looking at the source code for the pin mode function. We can see here where the output mode is defined. It sets a variety of items, but it doesn't set the drive strength at all. So that suggests to me that I could write a function that does set the drive strength and use that in addition to pin mode to make sure that I can get the high current output. Being a good citizen, I reported back to the forum once I'd solved the problem, just in case anybody else needed to know. So to recap my process a little bit, I built version 1 and it worked just fine right out of the gate. I built version 2 with a different microcontroller, and I observed some problems with the switching of the solid-state relay. I didn't know where to look, so I started measuring voltages. Just keep on testing and see if you're getting what you expect to be getting at each of the pins. So when I move my voltage measurement around, I'm seeing what I expect. And finally, when I moved it to the SSR, I saw a voltage that was much lower than I was hoping it would be. It should be a voltage that's up around 3 like it is now. Because I saw that voltage that I wasn't expecting, I went looking for what was causing the problem. I isolated the problem on a separate piece of hardware so that I could find out just how much power could I get out of those pins. And I saw a problem. It didn't match up with what we were getting from the product specification sheet. So I created a workaround with this switching transistor that let me solve the problem for the interim to make something that actually worked. That's good engineering. If the product doesn't perform up to what you were hoping for, find a way to make it work in the meantime while you go searching for an actual solution and better understand the problem. The problem turned out to be the software configuration of the hardware. It could only provide the high current output if we set the code up right. And by setting the code up right, I was able to eliminate the transistor from the workaround and go straight to controlling the SSR from one of the output pins on the microcontroller.